Latest in our series of webcheminars brought to you by Thieme. My name is Toby Reeve and I'm an editor of Science and Synthesis, which is Thieme's reference resource for synthetic organic methods. The general theme for today's topic is base metal catalysis, and coming up we have 4 great speakers who will be presenting some of their recent work. We're also delighted to be joined by Professor Naohiko Yoshikai, who will be chairing the session, and I will be handing over to him in a few moments. Before we begin, there are a few general comments about today's event that I'd like to make. The seminar is being recorded and the recording may be shared later on various platforms such as YouTube. You will receive a link to this recording by email shortly after the event. As the audience, you will be kept on mute throughout the session, but we do encourage you to submit questions for the speakers. So please type these into the Q&A window here on the GoTo platform, which hopefully you can see. And as many of these as possible will then be answered after each of the talks. If you wish, you can also include your name and affiliation with your question, and we will then try to mention these details when the questions are asked. Please also keep an eye on the chat panel window where you'll find information about the speakers and some links to content that they have published, including some reviews from Science and Synthesis that we are making free to read for a short time to celebrate this event. A quick word about the portfolio of publications and e-products that we offer. So at Thieme Chemistry, we specialize in publications and products that are related to synthetic methods and organic chemistry. And you'll be familiar with our journals, Synthesis and Synlet. And also we have fully open access journals, SynOpen and Organic Materials. So please keep these journals in mind when you're thinking about where to submit your research. In addition to our online reference work, Science and Synthesis, which I'll talk a bit more about later with a very short demo. Our other publications include a database of approved APIs called Pharmaceutical Substances, which includes information about applied synthetic routes. Another recent development to announce is the launch of a new open access journal, Sustainability and Circularity Now. So with the growing global awareness of the important issues that reports in this journal will be looking to address, we see this as being a key addition to the available platforms for publishing advances in these areas that are listed on this slide. A key aspect of the scope of this journal will be a focus on circularity as the next step in the evolution of green and sustainable chemistry, and will be open for submissions for this journal very soon, so in the last few months of 2023. Okay, so today's webinar topic was chosen partly to celebrate a recent addition to the Science and Synthesis content with the publication of 2 volumes of reviews on topics in base metal catalysis. So this series was edited by our chair for today's webinar, Professor Naohiko Yoshikai, and I'd like to take the opportunity on behalf of the editorial office to express our immense gratitude to Naohiko for his dedication and the very thorough approach in the editing of this series. So volume 1 was on copper and nickel catalysis, and this was published at the end of last year. And volume 2 was on cobalt, iron, manganese, and chromium catalysis, and we completed that volume this month. And many of the reviews from that volume are already online on ESRS as early view content. So in total, this series featured 34 reviews, and of course, we'd also like to thank all of the authors who participated, 3 of whom will be appearing later today as speakers in our webinar. And a bit later in the session today, I'll give a brief demo of the current platform of SRS and show you how the content of the base metal catalysis volumes can be found online. Okay, for now though, I'd just like to begin the session by introducing our chair for today, Professor Yoshikai. Naohiko was born in 1978 and raised in Tokyo. He received his BSc, MSc, and in 2005, a PhD degree from the University of Tokyo, under the guidance of Professor Eiichi Nakamura, and he then served as an assistant professor at the same institute. In 2009, he moved to Singapore to join the faculty at the Nanyang Technological University as an assistant professor and a research fellow of the Singapore National Research Foundation. In 2016, he was promoted to associate professor with tenure. And in 2021, he returned to Japan as a full professor at Tohoku University. His research revolves around the exploration of new reaction chemistry using transition metal catalysts and main group reagents for selective organic synthesis. So I'll now hand over to Naohiko, and thank you again for joining us today. And he can introduce.
Yep. Okay. So thank you, Toby, for kind introduction, and also thank Toby and Somia for this arrangement. So I'm Naohiko Yoshikai from Tohoku University. It's a great pleasure to chair this webinar.
Sorry, Naohiko, we lost the audio there for a moment.
Sorry.
That's better. That's a bad on. It's working again now. Yeah. Mm-hmm. Yeah, that's fine.
Okay, so the webinar on base metal catalysis featuring 4 distinguished speakers from Asian countries, 2 from China, 1 from Singapore, and 1 from Japan. So as Toby mentioned, this webinar was organized to promote the recently completed 2 volumes of Science of Synthesis reference library on base metal catalysis. So let me take a few minutes to introduce the background and the contents of this this reference library. So back in 2020, I was invited to edit an SOS volume focused on base metal catalysis. As you may agree, the definition of base metal is somewhat loose and may depend on the context. But we decided to focus on the Earth-abundant first-order transition metals, or 3D metals, ranging from copper in group 11 to chromium in group 6 of the periodic table of elements to achieve some coherence in the contents. And the project took actually quite a long time, but partly because of the COVID-19 and also my personal relocation. But I'm pleased to see that the project has finally taken shape thanks to the editorial office, especially Toby, Alex, and Karen, and also, of course, the great contributions from all the authors, including 3 of today's speakers. I mean, Professor Ming, Zhang Lu, and Tatsuhiko Yoshino. So I take this opportunity to express my sincere thanks for their great the outstanding support and contributions. So let me briefly introduce the contents of each volume. The volume 1, already available online, mainly focuses on copper and nickel catalysis. The topics are broad, ranging from cross-coupling, CH activation, alkene difunctionalization, and also functional group installation or manipulations, such as triformacylation, carboxylation, and oxidation, and functional group shuttling chemistry. The volume 2 mainly focuses on cobalt, iron, manganese, and chromium catalysis. In addition to cross-coupling and CH activation, which are also important topics in the volume 1, this volume also covers other types of transformations, including hydrosilylation, hydroboration, Lewis acid catalysis, CH oxidation, hydrogenation, metal hydride hydrogen atom transfer, or MHAT type transformation, and Nozaki-Hiyamakishi type reactions as well. So what makes base metals so unique? This slide summarizes some of the unique attributes characterizing the base metal catalysis. So base metals, compared to their heavier congeners, have some unique properties, such as smaller d orbital energy splitting, weaker metal ligand bonding, and lower electronegativity, smaller covalent radii, and lower reduction potentials. And such properties can often lead to unique reactivities, such as one electron redox, bond homolysis, and this one is the high oxophilicity of high-valent species and strong nucleophilicity of low-valent species, to name a few. Such reactivity can often lead to mechanistic complications, but at the same time allows us to exploit unique mechanistic concepts or design elements for catalysis, such as electron and atom transfer. And radical relay, redox active ligands and substrates, oxidatively induced reductive elimination, and ligand-to-ligand hydrogen transfer, to name a few. So, and furthermore, the unique property of base metal provides an excellent opportunity for the merger with photo and electrochemistry. And in this context, you are also encouraged to look into other recent SOS volumes on photocatalysis, dual catalysis, and electrochemistry. So with that, I hope this opening remark will be helpful as an introduction to the following invited lectures. So now let me introduce the first speaker of today's the webinar, Professor Lingling Chu from Donghua University. So Professor Chu obtained her bachelor degree in 2007 from Harvard University of Technology. And the same year, she began her PhD study with Professor Fenlin Qin at SIOC, where she focused on kappa-mediated oxidative triformylation. And in 2013, she joined the laboratory of Professor David Macmillan at Princeton as a postdoc to work on photoredox catalysis. And in 2016, she began her independent career at Donghua University. And her research interests focus on the field of the transition metal catalysis and radical chemistry. And importantly, she is one of the early career advisory board of Science of Synthesis. So today's lecture, the title is Asymmetric Radical Multicomponent Cross-Couplings via nickel catalysis. So Professor Chu, the floor is yours.
Okay, thank you, Professor Yoshikai, for the kind introduction, and thank you, Thieme Chemistry, also Professor Yoshikai, for the generous invitation. It's my great pleasure, personally, and also as a member of the SLC-ECAB, to participate in this wonderful webinar and to show our recent research progress in nickel catalyzed radical multi-component cross-couplings. Okay, so the slide is okay, right? Sorry. How to go to the slides? Oh, something's wrong with the slides. Okay. Sorry. Okay, so radical, as we all know, is also known as a free radical, is a molecule that had at least one unpaired electrons housed in the soma. So typically, radicals are short-lived, highly reactive, but also show also secondary activities to the classic cation and anion intermediate. So therefore, radicals are versatile and empowering synthetic intermediates in many important chemical transformations, including nature product synthesis and polymerizations. Recently, the rapid development in the area of photoredox and electrochemical synthesis has also driven a rapid advance of radical chemistry again. However, the notorious reactivity of the radicals also challenged the chemo and stereoselectivity of the radicals, and eventually the holy grail of the enantioselectivity control, because the radicals has low barriers for pyramid inversion. So, and chiral radicals are prone to undergo undesired and inevitable racemizations to get to the radical species, and also the rapid diffusion controlled radical recombination makes the enantioselectivity control of radicals elusive. We all know that chemists are always creative, right? So with a better understanding of the radical mechanism, chemists has made great groundbreaking achievement in developing catalytic radical mediated reactions by using Carl-Lewis acids or Carl organocatalysts to differentiate the radical addition, the facial approach of radical addition steps in these reactions. Another robust strategy profiles from the rapid development of transition metal catalysis, just as mentioned by Professor Yoshika, using first in the abundant transition metal catalyst, and the integration of the radical chemistry with the Carl transition metal catalyst has provided an efficient and powerful platform for developing new and efficient asymmetric radical couplings with high enantioselectivity control. These are indeed very impressive achievements. However, being a notorious open shell species, the development of catalytic in asymmetric radical couplings for these species remains a long-standing goal. And among these transition metal catalysis, we are particularly interested in the nickel catalysis because the low cost and also bound nature, and also the versatile reactivity and selectivity of nickel catalyst has shown in radical couplings. A challenge in the nickel catalysis remains in, as we can see here from this is a generally proposed reaction pathway for nickel catalyzed radical couplings. A key step is here. Alkene radical is captured by the Carl ligand ligated nickel-2 complex to form the nickel-3 species, and the nickel-3 species is expected to undergo reductive elimination to deliver the Carl products. However, nevertheless, complicated issue is that the nickel-3 species is prone to undergo a reversible nickel carbon bond homolysis to regenerate the alkyl radical and the nickel-2 species. And this reversible process makes the expected stereoselective radical capture process inefficient. So the whole transformation of these radical couplings has to rely on the final reductive elimination to deliver the initial enriched products. Of course, this characteristic reversible homolysis process has inspired chemists represented by Greg Fu, Sarah Riesman, as well as others to develop many elegant initial convergent cross-couplings and cross-electrophile couplings. Indeed, very impressive. We also have to realize that this reversible feature also poses more challenges to develop more efficient and asymmetric radical coupling modes. We just want to use these modes to develop with easier and higher precision control for the efficient asymmetrical radical couplings. So to try to conquer this challenge during the last several years, we have developed two strategies we called chelation strategy and sensitization strategies to try to provide alternative or more complicated stereoselective control modes for the radical couplings. In the chelation strategy, we expected that the chelation between the pendant functional group and the nickel would facilitate the alkyl radical to stereoselectivity add to the nickel centers to form a nickel-3 species. And the chelation also is a benefit for form a more rigid nickel complex with favorite reductive elimination, thus may help to impeding the reversible nickel carbon homolysis. In the sensitization strategy, the photoexcitation of the planar ground state nickel-2 complex with visible light will bring the bring the Nic2 species from its planar to its excited state, and the excited state is tetrahedral. So the change of the geometry of the nickel complex would might allow for stereoselectively radical capture process. Also, we all know that the photoexcitation would enhance the reactivity and enrich the selectivity by while the single electron transfer or energy transfers, and also more importantly, the stereoselective control at the photoexcited state of the metal centers remained elusive at the acute state. So back in 2016, when our group founded, we were particularly interested in the multi-component cross-couplings, because this kind of reaction modes can forge multi-component chemical bonds and enhance synthetic efficiency by building up highly complex and functionalized molecules by using simple starting materials. And we expect that the radical species would bring more distinct and reactivities and selectivities to this kind of multi-component reaction modes. However, during the last decades, this interesting area of kind of radical multi-component cross-couplings is proceeding slowly, because in this system we can easily see that more than one types of radical species and different kind of the radical species is involved. So it's kind of quite challenging to using one single transition metal catalyst to tune the chemo region and selectivity of this kind of radical species. So we wanted to focus on this kind of multi-component radical component system to test our proposed chelation and sensitization strategies to tune the reactivities and selectivities of radicals. Next, I will show several examples to illustrate we have developed during the last several years to demonstrate our reaction design. For the first one is the asymmetric three-component radical couplings of non-activated alkenes. The reaction design is simple. Alkene radical is added to the alkenes to form a secondary non-stabilized alkene radicals, and with the chelation between the functional group and the nickel, the alkene radical would be expected to selective captured by the chiral-nickel complex to form the nickel-3, and then undergo reductive elimination to deliver the final three-component or symmetrical coupling products. And as we mentioned previously, how to achieve the stereoselectivity radical capture step is important for the success of this kind of three-component coupling reactions. So after some initial trial, we chose the endoleocarboxylic acid-derived alkene esters as the template substrate, the polyalkyl aldehydes as the radical precursors, and iron bromide as the coupling partners, and to explore the possibility of this kind of three-component reactions. And after some initial trial, we were pleased to find that with the bioxylenton alkene substitute bioxylenton, we also called biox ligand, we are able to achieve the desired three-component coupling products with promising results, and using the newly designed seven carbon or nine carbon alkene substitute non-group substituted by ox with the chiral ligand, we are able to achieve the three-component couplings with high yield and high initial selectivity control. And also interested in the commonly used stereologically demanding chiral ligands such as PiBox, such as box, and filled with no products at all. This result also implies that kind of different reaction pathway could be involved in these reactions. So with the optimal reaction condition on hand, these three-component radical couplings also showed a wide range of substrate scope and with excellent functional groups and a wide range of each of the three component area highlight, alkene highlights, and then non-activated alkenes can undergo efficient cross-couplings under the optimal conditions to deliver the final initially enriched products with high yield and excellent EEs. With the carbenzolic esters on hand, we are able to synthesize a number of other carbenzolic motifs easily, and this kind of compounds is not easily accessible via other known methods. And this chelation strategy can be applied to the two-component radical couplings between the non-activated alkyl iodides and the bromide, and to deliver the final products with high excellent yields and ease, to further showing the effectiveness of these chelation strategies. To further think out the intriguing role of the chelation group in these strategies, we do some control reactions, and with the alkene ester could form the 6-membered nucleocycles. We found that enrich the electron using the more electron-rich aromatic substitute the carboxylic acid led to higher initial selectivity control. On the other hand, if we enlarge the ring size of the nucleocycles by extending the carbon trace to from 6 to 7, or getting rid of the chelation group, led to significantly decreased or even no initial selectivity control. So these results further confirmed that the important chelation effect in this system. Here is our proposed reaction pathway for these three-component asymmetrical coupling reactions of alkenes. And due to time limits, I'm not going to bother you with the details. And the key step is here: the alkene radical with the chelation between the functional group and the nickel. The alkene radical is expected to undergo a stereoselective radical capture to give the nickel 3 species, and then undergo reductive elimination to deliver the final products. And using this strategy, we are able to achieve the first example of the carbon alkylation of beta gamma alkene ketones by using alkene halides with the coupling partners in the presence of nickel cord and the simple second butyl substitute that by ox ligand, and this chemistry also demonstrate a good of substrate scope and with high initial selectivity control. We also found that the addition of the benzoic acid is important to enhancing the whole reaction efficiency, and we speculate that the key 5-membered nucleocycles intermediate could be important to achieving the high initial selective control for these kind of the carbon alkylations. Our second strategy is the sensitization strategy. We're using visible light to further excite the planar ground state nickel 2 complex to its excited state, and the change of the geometry of the expected or stereoselective radical capture step. Also, less explored, it is known that the ground state planar integral, especially with the bidentated ligand ligated area nickel 2 complex, can undergo further excitation to reach its tetrahedral excited states. And even in the absence of the extraneous photocatalyst, and the excited tetrahedral state of the nickel-2,3 is long-lived and also showed diversity reactivity in many photoredox and nickel-catalyzed transformations. So we expected that the radical capture by the photoexcited tetrahedral nickel-2 complex could be stereoselective, and then finally enabled the three-component radical couplings between the alkenes, array halides, and alkyl traveloboroids, while synthetic photoredox and nickel catalysis to deliver the three-component coupling products. With this simple thought in mind, we began to explore the possibility of this reaction design. Pleasantly, we found that using the simple iridium-based photocatalyst and carboxylic nickel-2 complex with the catalyst combination, and under the irradiation of blue LED, we are able to develop the three-component couplings between the alkylates, alkyl traveloboroids, and iron bromides to deliver the expected alpha carbon arylated chiral enriched products with good yield and excellent ease. And this three-component reaction demonstrate excellent substrate scope and with excellent enantioselectivity control. And this result alpha-related carbonyl compounds are important skeletons present in many biologically active compounds, and because the chiral center is sensitive to the basic conditions, say this photoredox and nickel catalyzed protocol provide a more benign and redox neutral protocol for accessing this synthesis is valuable structure motifs under mild conditions. With another synthetic advantage of the multi-component reaction mode is that allowing us to modulate and easily access to a library of the valuable products. For example, we can just simply change the structure of alkyl traveloboroids and using the simple alkenes and array bromides to easily forge a number of derivatives of the fulviopropane with high efficiency and excellent enantioselectivity control. And we also can using this chemistry to quickly synthesize the lead compounds of the pergalentins by using simple starting materials, while 3 steps, and this chemistry only takes 3 steps, much shorter than the previously reported routes. So we also did some mechanism studies to try to probe the reaction pathway. Firstly, the radical probe reaction with cyclopropene alkenes and temples indicated the involvement of alpha carbonyl radicals. And we also collaborate with Professor Osvaldo Gudrazzi, now at Texas A&M University, to try to better understanding the chemo and the stereoselectivity in this 3-component mode. And we found that under the catalytic condition, the alkyl radical addition rate to the alkenes is much faster than the one to the excited triplet array nickel-2 complex, thus securing excellent chemoselectivity in this 3-component mode. And we also found that also, as we expected, that the radical capture by the tetrahedral excited array nickel-2 complex is the stereodetermined step for this asymmetric reaction. NCI analyze also disclosed the important non-covalent interactions between the arrays or the chiral ligand is important to achieving higher enantioselectivity control. Also, same as previous report, we found that the NiCO3 species generate from the ground state NiCO2 is also prone to undergo reversible nickel carbon bond homolysis, thus posing more challenge to achieve the higher initial selectivity control. Here is our proposed direction pathway for this synergistic photoreductant and nickel chemistry. Simply the photoexcited photocatalyst undergo a single electron with the tertiary with the alkyl travel laboratories to release the alkyl radicals, which then add to the alkenes to form the alpha carbonyl radical. For the nickel cycle, we propose start from the nickel 0, oxidative addition of nickel 0 with array bromide to give the ground state NiCO2 species with the irradiation of the pre-LD. It goes to the excited state, and the radical capture of the excited state by the with the alpha carbonyl radicals will deliver the NiCO3 and then undergo reductive elimination to deliver the final product and the NiCO0. And finally, the single electron events between the reducing photocatalyst and the NiCO1 will close the two catalytic cycles. As we mentioned previously, the important application of the photoexcited photocatalyst that can not only engage in single electron transfer with organo or organometallic species, but also can engage energy transfer with them. So, they also bring some more exciting and unrevealed reactivities. One important application of this kind of energy transfer is tricking the alkene Z2E isomerizations. So that means we can using the tuning the structure of the photocatalyst to achieve the both cis or trans alkene products. For example, in this three-component carbon alkylation of one alkenes, we can easily using these two photocatalysts to achieve the initial selectivity, the initial enriched both cis and trans initial enriched oleic esters by using the two photocatalysts. And for the initial selectivity control of the alpha phosphine carbon center, we found that the use of the Chiral by emit the ligand with electron deficient array rings substitute is optimal for the control of the sp3 carbon centers. For the finger out the ZE selectivity control, we do some mechanism studies. First, the star warmer quantity studies indicated that the photoexcited catalyst is significantly quantized by the alkene bromide, while the redox potential of each of them are unmet. So we expected that the energy transfer between the photoexcited catalyst and the alkene bromide could be involved. And also the control reactions with both trans and cis alkene bromide. Also, the calculated triplet energy supports our assumption. Simply to say, in this system, PC1 with a bit of higher triplet energy can engage electron transfer, energy transfer with the trans alkene products, and finally deliver the cis alkene products, while PC2, which has a lower energy transfer, can only afford the trans products. So that allows us to modulate the initial ZE divergent synthesis of these valuable alkene oleic phosphonates. Also, DFT calculation indicated that the interaction between the phosphonate and the alkene will direct the alkene radicals stereoselectivity to add the triplet, the alkene alkene nickels, and this step is the stereodeterminant step in this carbon alkylations. So with the optimal mining condition, we can easily simple using two simple photocatalysts to achieve the ZE stereodivergent and enantioselective carbon alkylations of 1-phosphate to deliver this allylic phosphate with high stereoselectivity and enantioselectivity control. And we can use this chemistry, this Chiral phosphate, to easily synthesize a number of biological actively related alkyl or alkene phosphonates with easy manipulations. So this sensitization strategy allows us to develop a number of symmetrical carbon alkylations, of carbofunctionalizations, of alkenes, and also we can use this strategy to tune the reactivity and selectivity of alkene radicals just by generating via the radical addition to the readily available to the alkynes. We have, as shown here, we have developed several systems of the stereoselective and even stereodivergent functionalization of alkenes, including terminal and internal alkenes, to efficiently construct these substitute alkenes with high efficiency. So, okay, last but not least, I would like to thank you, my students, for their hard work, collaborators for their excellent contributions, and founders for the financial support. And thank you for the listening. I would be happy to take any questions.
Thank you very much for an excellent talk. So, well, now we are in Q&A session, so I'd like to accept questions from the audience or even panelists. Seems that there is no question at this moment, so let me start. So seems that in your reaction, this Biox type ligand is very effective, right? So
yes.
compared to the conventional box type ligand. So what kind of electronic or steric nature of this ligand is so special for your reaction, or the reason why the box ligand fails to promote your reaction? Do you have any comment on that?
Thank you for your questions. And according to my understanding, probably because the bioxylic is kind of redox, is non-redox active, so it might be effective to participate in the radical couplings with this kind of my chemistry. And also, yeah, that could be the main reason for this, based on my understanding.
So you mean that the ordinary box type ligand have a redox active property, you mean?
Yes, and yes, because especially in the, because based on our reaction design, the radicals is kind of selectively captured by the bioxylic and the ligated nickel complex. So yes.
Okay, thanks. Any question? From the panelist? Okay, so another question. Can you show the page 35?
Page 5?
Yeah, no, 35.
35, okay.
Yeah.
Is this one?
Oh, yes. So on the top scheme, you show that the ground state nickel 2 complex can capture the radical, but it's reversible, right?
Yes.
Yeah, so tentatively from nickel 3 species, but it's undergoes the reversible homolysis.
Yes.
I was wondering what is the difference upon radical capture? I suppose that I mean the species on the right side can be the same as the species on the left side.
According to my understanding, is that under the irradiation of the photo under the below LED, the ligated area nickel 2 complex will be promoted to the tetrahedral state. It's kind of the triplet state or D3D state kind of. It's not a planar. So if the radical added to this kind of the nickel 2 complex is efficient to undergo the final reductive elimination to deliver the final products. Also, if it added to the planar nickel complex, it may undergo reversible. And we have this slide. We as well also do some calculation to show that to support that this. Of course, this nickel 3 is same one with the generated from the nickel 2 is kind of is not able to undergo effective reductive elimination to deliver the final products. Other than instead, this species is kind of to release the Alkene radicals again. So it's the same constraint with that. But this is also same for the classic inertial convergent chemistry, especially inertial convergent cross-coupling and cross-electrified couplings. So we're using the racemic key highlights products can deliver the fine with the chiral ligand can deliver the fine inertial enriched products, right?
So you mean that so two nickel 3 intermediates their coordination
the geometry of the yes.
Okay. Thank you. Oh, so there is one question from Kong Fei. For the internal alkene, does it work with internal alkene? So your reaction, does your reaction work with internal alkene?
Okay, yes. The synthetic challenge by using the internal alkene is, of course, is much bigger than the one I showed in terminal alkenes. But it also brings more direct centers with more two direct centers. So the inertial selective control of these direct centers is more challenging. But because based on our condition, we are able to achieve the difunctionalization of internal alkenes with kind of direct selective or even inertial selective. But I just didn't show here, and we haven't published it yet. But yes, we are able to achieve it now.
Thank you very much. Any other questions?
Hey, Lingling, I have a quick question.
Hey.
This slide, you got the stereo determining step, which is the rate determining step. Is that the reduct elimination step? Which is the rate?
The rate determining step? Yes. It should be not the reductive elimination because this nickel 3 species is prone to undergo faster reductive elimination. But if we didn't actually, we found that the in this specific addition, the rate determining step and the stereo determining step is the same one. But we also found that the alkene radical addition to the alkenes is not kind of smoothie. So it also have some energetic challenge here.
Is that a possible?
Yes.
The rate determining step is the generation of like a tubular radical.
If from the SEG event?
Yeah. Is that possible?
based on my understanding, it probably not, because the generation of the by the photoexcited catalyst is kind of phasor, and then the alkyl radical to alkenes to undergo the classic Gibbs addition, right? But I don't think so. But in my with my understanding, and more challenge here is the nickel mediated cross coupling, the final cross coupling. Yeah.
Okay, thanks.